Hi, short start. So I'm Franc ois Charton, I work in Meta, and my talk is titled Transform Meet Lyapunov. You know, it's one of the famous memes, together with X is all you need, or the unreasonable effectiveness of Y, you got X meets Y. So I'm going to talk about Lyapunov function, but what's important is the subtitle. What I try to explore is what does it really take to solve a hard mathematical problem with AI? Because so far, a lot of research doesn't focus on hard problems, but easy problems to prove that AI can solve. So I'm going to talk very quickly of the mathematics. We're talking of dynamical systems. So a dynamical system, a system of n equation in n variables that can be represented by a function that provides you the gradient at all points. So dx on dt equals f of x. And if at some point x0, some point in phase space, I have f of x equals 0, then I might have an equilibrium there. And there's a very cheap way to know that. The system is locally stable, or some call it asymptotically stable, if all the complex eigenvalues of the Jacobian at x0 have negative real parts. Okay, and this is known math. And in 2021, it was published in 21, worked for 2020, together with Amaury Hayat and Guillaume Lampe, we proved that transformer can actually learn that. So you can show a system, provide a transformer with a system, so a function f, and train it to give you the eigenvalues, the largest eigenvalue, or 1, 0 to say it's stable, it's not stable, something like that. This works. So today I'm interested in a much harder problem, which is the global stability of the dynamical system. So the question is that now you have a stable equilibrium in x0, which I was supposed to be the origin. If I start close to the equilibrium at t0, can I guarantee that I stay close to the equilibrium? So if I start in the blue ball, am I staying in the red ball all the time? Yeah, and this is an important problem, because it's linked to, you know, it's been studied by a lot of mathematicians over time. It's linked to that n-body problem that is represented here. And I was very proud of having a slide with Poincaré together with Netflix. So there you go. But it's an important problem in dynamical control theory and all that. And there's a result on global stability, which is due to Lyapunov, the man here. And it's an old one. It dates from 1892. And it's a very interesting result, which says that if you can find a continuous function v such that v has in 0 a strict minimum and v is infinite at infinity, and you have this relation, which basically says that the gradient of v points away from the vector f, you know, the direction of the gradient of the dynamic at all points, then the system is globally stable. And if you start close to the origin, you stay close to the origin. So v is some kind of entropy-like function that needs to decrease. And if you can find such a function, then you can show that your system is stable. So it's really a big thing. So this is, I think, a sufficient condition, but it was proven throughout the 20th century to be necessary in a fairly wide, you know, set of systems. So you could say it's sufficient, but close to necessary, maybe, something like that. Anyway, I will also talk briefly of a weaker form of this problem, which is called barrier Lyapunov function. So if you relax, you see here you got 3 conditions. Sorry, I told you wrong. So here you got 3 conditions: strict minimum, infinity, and the dot product condition. If you relax the first one, the strict minimum, and you accept v of x has a minimum, but not necessarily strict, in 0, and you keep the 2 others, v is what they call the barrier Lyapunov function. And the barrier Lyapunov functions splits the phase space into several, usually 2 groups, two areas, which are not necessarily compact. And if you start in an area, you stay there. So you can think of it as kind of a non-compact version of Lyapunov. Basically, if you have a barrier function and you have some subspace, and if you start in this subspace, you stay there. Okay, so that's a weaker version of the theorem. We'll see it, you know, at the end.
Subspaces are related to level sets of V or something?
Sorry?
The subspaces are related to level sets of V?
It's the level sets of V. Basically, V equals 0 split the thing into subsets. And the V equals 0 surface is what they call the barrier. Okay, so Lyapunov theorem is great. It's an absolutely great existence result. But the funny thing is that it's absolutely non-constructive. And there's no systematic way of finding V from F provided there. There's not even a way to prove that V exists for a given F. You know, most dynamical systems are not stable, globally stable. But you cannot prove that. At least you would need to exhibit a Lyapunov function to do that. There's not a weaker result that would allow you to do this. And today, 130 years after Lyapunov, the state of the art is that there's still no systematic method for finding Lyapunov function. You can spend a whole PhD finding one. That's kind of the state of the art for global Lyapunov functions. There exist numerical methods for very special cases. So specifically, if you have a small dimension in the phase space, and the function f is a polynomial of relatively low degree, like 3, 4 max, usually less, and v is a sum of square of monomials, okay, so positive because of that, then you can calculate a solution, and there's a set of tools for that called source tools. It's very computationally intensive, so it works on very special case and small dimension. But it doesn't work on all polynomial, not even all small polynomial. In 2018, 11, Amadi and others showed that there are stable polynomial systems which don't even have a source Lyapunov function, sum of square Lyapunov function. So it's not even good on the set of polynomials.
I'm confused because you have some partial result for finding the Lyapunov function, but it contains a hypothesis that the Lyapunov function is a sum of squares.
Yes.
So what happens if it's not? You just don't find it?
Well, you don't have a tool to find it. Again, it's non-constructive.
You only find it if the test.
Yeah, source tools, basically you have a numerical method if you are able to have a sum of square and it's polynomial, because in that case, you've got, sum of square methods that can save you and find something numerically for you. But that's the only case, and it's not even the case for all stable polynomial systems. It was thought to be so until 2011. And since a few years, there's been neural networks for some sort of weaker problem that is robustness with respect to small perturbations. So most of the time when you have those problems, you're actually doing control theory. You're not interested to know if a system is stable. You have a system which has a parametric aspect, which is the controls you can manage, and you want the controls to keep the system stable. So you want to select a control so that the system controlled is stable.
Question?
Yeah.
Quick remark. There is another method. I used to do it in my previous lives. There is a method called Lyapunov focus numbers, which essentially is like the next step. And what's interesting about it, those focus number or focal numbers are computed using Grafner basis. So you can do it for polynomials. Okay. Another remark. Just polynomials are extremely complicated. Apparently, most of the stuff that can happen in smooth and analytic dynamical systems happens in polynomial. That's why we have Hilbert 16. So there is this very heavy weight method using Grafner basis to compute those numbers, which is essentially expansion in polar coordinates.
Okay, thank you. I didn't know that, but thank you very much. And there have been, so with respect to small perturbations, so if you have a control system, but you can guarantee that the perturbations are infinitesimal, so this typically happens in robotics. Then there are neural networks that basically estimate the local values of the Lyapunov function as a black box and use it to provide approximation of f for small perturbation. So this works. But of course, there are many cases where you really want global functions. Think of epidemiology. You've got illness. You absolutely don't care of small intervention, like a few people being sick. Think of flood control. Yeah, a little rain, less or more, is not what you care about. Transportation, same thing. So the global case remains an important thing and an important open problem. So the paper I'm going to talk about is, it's not yet published. It will be on arXiv in, I think, next week or the week after next. It's done with Alberto Alfarano from Meta and Amaury Hayat from École des Ponts, who's a mathematician. And the idea, it's always the same. We want to train a language model to predict V from F. So basically, I want to show a lot of examples of F and V to my model. And so that the model is going to learn some kind of pattern that might exist to translate F into V. And then when I train a model, I will shoot an F that a system that I'm interested in, and the model will provide me a V. At least that's the plan. Could that ever work? Well, a couple of years ago with Lyapunov, we managed to do symbolic integration this way, and it's exactly the same kind of thing. You got a function, you want another function, it's the integral. And we showed that, simple transformer can do this as well as Mathematica. So if it's possible, why not try Lyapunov?
I mean, and again, the integral, you could just sort of take the derivative and get the pairs. This.
Generation.
Yeah, so
this is about half of the talk, so just wait. Because this is the hard problem. So basically, here's the program. There are 5 steps. Step 1, I'm going to need to generate a lot of training examples of pairs of F and V. Then I'm going to need to encode the F and V sequence of words in some language so that the language model has sentence that it can process. Then I'm going to train a model to predict V from F. And then once the model is trained, I take an F, I generate as many guesses of V as possible. It's easy for a model to do several guesses. Let's use that. And I need to test the guess and hope for the best. So I'm going to talk about those 5 points, excluding the one, which is the hard one. So I'm starting from 2, because this is the easy stuff. So how do you encode F and V as sequence of words that the language model can process? Well, F is a system of n function, V is a function, so you need to encode a function. So you got functions like this. These functions can be represented as trees like those. The parse trees in computer science, abstract syntax trees. And then the trees you can enumerate to make them sequences. And there you go. So it's very easy to represent those problems because they're all symbolic problems. So turning sequence of symbols into sequences is not really a problem here. Training a model, so it's a totally vanilla transformer, sequence-to-sequence model, 8 layers, 640 dimension, 8 heads. It's probably 150 million parameters, so we are nowhere near a large language model. It's a small language model. It's trained to predict the next word of V given F. So from F, you predict V0, the first word in V. And from F and V0, you predict V1, and you rinse and repeat until the model outputs a period, something that says end of sequence, and you're happy. How do you train it? You train it to minimize the cross entropy between the next token and the correct value in the training set. So this is supervised training. You start with random weights and you adjust them using gradients every time the next token is not correctly predicted. As I told you, this is totally basic ML. There's nothing bright here. The cross entropy is a fun thing because it has nothing to do with mathematics. So the model here does no mathematics, it does language. For the model, this could be 2 weird language that you're translating into. It could be any kind of problem. The model has absolutely no idea that this is mathematics, and the only mathematics the model is going to see are those sequences of F and V that are put into it. Then the next thing is to generate guesses of V. So we're using a trick called beam search. Yep.
Just curious, when you are selecting your vector fields, were you enforcing that the critical point is non-hyperbolic, or was there like a linear tool in the critical point in your examples?
So when I generate the data, you will see when I generate the data, I'm using always the same critical point, which is 0, and I generate data with F and V with a critical point at 0, and we check that the critical point exists.
Mm-hmm.
So we're trying to work on stable system, but we'll see a case where we don't. So we generate guesses. So the idea, the model, the transformer predicts a solution, but basically it predicts a probability on symbols of the solution. So instead of predicting one symbol, the most likely symbols, you could predict the n likely, and you would get n chances for the first token. And with that, you got n square second token, but you could look at the n most likely about the n square and so on. So this is just a trick so that the model, instead of having one guess, you give it 10 guesses or 50 guesses. It will obviously improve the result. And finally, you need to test. The model predicts something. Is it a Lyapunov function? Is it not? So this is the only place where we're going to use mathematical software here. And you need a software. You need a verifier. If you don't have that, this approach doesn't work. So what you're going to do, you just decode a sequence representing V, all the tokens, into one function. And then you need to check those 3 conditions. These are what makes a Lyapunov function Lyapunov. So we started using numerical methods, so solvers. We've been using SMT as well. They give similar results. to prove that the Lyapunov conditions hold. So the thing is that the system are not 100% perfect. If they say it's positive, it's positive. But they might fail, and it's positive and we don't know it. So we might have false negative. We don't have false positive, but we might have false negative. So all the results we have are underestimate the accuracy. So we might miss a correct Lyapunov function, but unfortunately, there's no way out of it. This is the price we have to pay. Okay. So now I come to the real subject, which is generating pairs of F and V. So how do you generate the data for a problem like that? So in an ideal world, we would generate a random stable system F, right? And then we would use some solver, some magical solver. We would have to calculate the Lyapunov function, add the pair FV to the training set, rinse, repeat 10 million times, and we're happy. But this doesn't work on many accounts. The first thing is generating a stable system. We're not even capable to prove that a random system is stable. So generating a stable system is just impossible. Second, computing the Lyapunov function, well, we've seen that. The only way we can do that is on very, very simple cases. And we want to be the state of the art, not just emulate it. So there's no interest in doing that. So we can't follow that. Well, we can do it on source tool functions, and we will do it for test purpose, but that's not what we want to do. So we're going to use a method we introduced with Guillaume on the paper in integration using derivation, which is a backward method. So the idea of the backward method is very simple. Instead of finding the solutions of random problems, we're going to find the problems associated to random solutions. Okay, so in this case, I'm going to sample a function V and construct a system F, which has V as its Lyapunov function. So you remember, there are three conditions for V and F to be a Lyapunov function. Two conditions are only V condition, they're intrinsic. V must have a strict minimum in 0, and it must be infinite at infinity. And the third one is the thing that associates V and F. So I need to first generate a V that verifies this, and then to create an F that verifies this given V. So I want to select a random function V, which would be a C1 function, a continuous function, with the strict minimum in 0, which is infinite at infinity. And then I want to find a random system, as random as generic as possible, such that this is verified. So before I speak of that, there's a couple of constraints on backward generation. And there's a number of difficulties that we're going to see here. The first thing is that we want V and F to be as generic as possible. I don't have a good working definition of generic, but if you want to train the model on Lyapunov function in order to learn new Lyapunov function, you need to have your examples to be as diverse, as generic as you can. So, for instance, when you want to sample V from the class of continuous function with a strict minimum at 0 and infinite at infinity, I'm told that sampling a function with a strict minimum is a very hard problem. You need to work in a smaller class, because the whole class of function with a strict minimum at 0, it's, I don't know if it's an NP hard, but it's a hard problem, really. For V, we would like to find F, but not just one F that verifies that. An F that is sort of as variable as possible given V. So we want to select V and F from the largest possible class possible, and with as little bias. Again, I don't have a good working definition of bias, but I think you understand what I mean. Possible. The idea is that my V and F must be as, generic as I can make them. There's a second constraint, which is even worse. We really want the model to learn to solve the Lyapunov function. Now, there's always a risk that the model is not going to do that, but it's going to reverse the generating procedure. I have a technique for generating P from F. And if I'm not very, very prudent very, very careful about it, the model might learn the generating procedure, or the inverse of the generating procedure, and not Lyapunov function. To give you a very trivial example of how this can happen, suppose you want to calculate the roots of polynomials with integer coefficients, okay? And so it's very tempting to use backward generation. You got 3 roots, 2, 5, 7, you can calculate this nice polynomial out of it. But of course, you don't want to show the model this as in the training set, because the model is not going to learn to simplify. It's going to learn to read those. And that's all it will do. You will solve a ridiculous problem instead of the one. In that case, it's very easy. You just develop and simplify, and you're back on track. But you can understand that many ways this can go terribly wrong when you have a generated method. So a different way to say it, and that we will see a lot, is that what I want to do is that I want to prevent the generation method from leaking information about the solution into the problem. Exactly as you say, you know, sometimes you leak information, data contamination, you leak information from the test set into the train set into the test set. This is the same idea. The general idea is that naive methods will not work, and we need to some extent to obfuscate to generation method, to make the generation method not only generic, but also not reversible. And these are slightly different things. Another point, and there was a paper a couple of years ago about that, is that in general, you cannot guarantee the absence of such leaks. The best you can do is minimize and pray for the best. We'll see that we can have a pretty good idea that leaks don't exist, but you cannot guarantee it by looking at a method, by just selecting a method. So let me go through the steps. And you know, the goal is not for you to memorize the step, but it's just to show you, you know, what it takes and how difficult it can be. So we want first to generate V. We want V infinite at infinity with a strict minimum in 0. I put strict minimum in red because this is hard. It's difficult to enumerate the function with a strict minimum and to sample them. So the way we do it, it doesn't come from us. So many people have been using that. You decompose V into V proper and V cross. V proper is a function with a strict minimum in 0. And in some limited class where we can guarantee the strict minimum. So typically transforms, polynomial, things like that. And V cross is just non-negative unbounded. So this is a very large set of function. So specifically for V proper, the way you do it is you sample a positive polynomial. So you take the entries of a random positive digit matrix, you get a polynomial that is positive. You could use that, but you would limit your V to just polynomial. So that's not a good idea. But the thing is that if this one is strict, if you transform it with any generic, you know, increasing function, it will still be strict, right? So you can sample in a very large class a transformation to transform it. You could even multiply it by random positive function. So you see, you get an expression like this, which is guaranteed to have a strict minimum in 0, which guaranteed to be infinite at infinity. And then for V cross, it's a sum of square of bounded functions so that it has, you know, negatives and all that. So you get a slightly complicated way of generating a non-negative, a function with a strict minimum at 0. It gets interesting when you want to generate. So now we have V in a fairly large class, not the largest possible, but fairly large. Now we want to generate F. And for this, we have only one constraint, which is this one. So if you look at the constraint, there's an obvious solution, which is minus nabla V, right? If I took F as minus nabla V, then this would always be negative. And I'm done. But of course, it's a naive idea, and it's a very bad one. Because if you do that, finding V from F just means integrating. So it's not an easy problem, but we will be, if we do that, the model will be trained to solve a different problem than the one we want to solve. Okay, so you cannot do that, but you can modify this solution. The way to modify the solution is you take the nabla V here, and you multiply every single coordinate of it by a positive function to the square of a random function. Then you're completely, since the random function vary all the time, you're completely obfuscating the thing. But it's easy to get convinced that, you know, the inequality still holds. So we get, with that, we still have the inequality, but it's no longer possible to solve that by integration. So we eliminated this hole. Okay? We can actually do better in terms of genericity, because if I add to F a vector W such that, you know, that is in the normal hyperplane to V, so the hyperplane perpendicular to the gradient, then this will not change. This will not change the Lyapunov condition over there. Sorry. This will not change this Lyapunov condition because I'm adding 0. Okay, so if I do that, I can add a vector and make the function even more complicated. So the way you do that is that you could generate, once you have the gradient, you could generate a base from the gradient and take a random vector out of it by having a random function, etc., on the base. Okay, so this makes your function f is now a transform of the trivial solution plus a random vector that will add nothing. And we claim that this is pretty much as generic as you can get in generating f. But just to show you, because I'm showing the pitfalls, but we fell in every single one. And just to show you how wrong this can be, I need to generate a base of f. Sorry, suffering. I need to generate a base for this hyperplane or for this space. So the temptation would be, okay, I need to have a base, so let's use Gram-Schmidt. I got computers, I got everything for that. Well, don't use Gram-Schmidt. Don't do orthonormal base, because if you do that, you're going to see a term like this appear in order to normalize. So it's not, you cannot find V from the norm of nabla V. It's not possible, but it still leaks a lot of information about V, and you don't want that. So what I'm trying to say here is that it's very easy to have, and the thing is that those elements will appear in the form, and there's absolutely no chance that they will simplify away, or very, very little chance that they simplify. Things usually don't simplify. And of course, this leaks more information. So we started trying to do something right, generate an orthonormal base and a random vector, and ended up abandoning all, being shameless and going for a non-orthogonal base, not even orthonormal, nothing, and try to make the EIX as simple as possible so that they simplify well. Okay, so the summary of this long presentation of how complicated it is to generate it is that you can generate here a function, V, which is a sum of two functions, and get an F there, and it's guaranteed that everything verifies the Lyapunov condition. The good thing with this approach, you've seen every time I say I'm generating a random function this, generating a random function that. This is very important because the random functions, by using those random functions and by selecting those random functions in different classes, you have controls on the data you produce. You can decide that how to generate V and F to be polynomials or non-polynomials, or to have a special form. So this way you get, you can generate data sets of all kinds of sorts, which respect a number of constraints that you would like to observe. So finally, I'd like to say that we had to take a lot of steps, and this project took several years just for the generation. I mean, most of the work was generation. Lots of steps were taken to ensure that the generating process doesn't leak information, and we are very proud of it. But we have no guarantee. In the end, we don't know. Yep.
One thing that you might have done a good job is if you use the test set. And V is probably not.
You're again anticipating my next slide. Yeah, Leon.
So we're developing complicated V's and slightly more complicated F. In Baxi, I would like to take a simple F and get the possibility.
So this is a very good point. It goes even beyond that. The thing is that generating a random system and calculating the Lyapunov function has a certain distribution. Generating random distribution and calculating systems, even if my generating system is great, absolutely guarantees that the train set distribution is not the test set or the distribution I would like to have on my data. But this is a drawback of the backward method. There's no way out of it. So I'm adding here an out-of-domain distribution problem that I will have to solve at some point. I'm making things hard for the model because the generalization I want is out of domain.
You could subsample this thing, right?
Yeah, you can, but then, what guarantees that you're not again leaking stuff because of the subsampling. So, but we'll see that there are ways out of that. So in the end, we generate training sets. So we generated two backward training sets, a polynomial training set of 1 million function, backward generated polynomial system of 2 to 5 equation. Why polynomial system? Because I want to compare myself to source tools. This is the only test set I have. And then a non-polynomial system of 1 million. So in that case, what I call non-polynomial system are polynomials of general function. So trig polynomials or a polynomial where the monomials would be, functions including exponential, logarithm, whatever. So it's not exactly the most non-standard function you could get, but I'm told by Amaury that it's a fairly large and interesting class. But we could do more. I mean, it's not very difficult. It's always the same method. But basically, we have two training sets of 1 million data. And we use source tool to generate forward training set for test purpose and to check how it works. So source tool is very slow. So we could generate 100,000 polynomial systems on source tools. It took several weeks. And we could generate, this is why I talk of the barrier Lyapunov function. This is much easier. So we could generate 300,000 polynomial system for which source tool can find a barrier Lyapunov function. So these are polynomial systems that source tool can solve, can reply. And what you have to remember, these ones are the Lyapunov function, and this one is a different but very related problem. And we'll see how we use this. So the first thing we do is very standard. You train your models and you test them on held out sample from the same distribution as the training data. So if you look here, you can see that the forward data set basically on the barrier and Lyapunov function with the batch size 50 achieve 98% and 88% accuracy. So the models learn, the polynomial models learn well, they're forward generated. So, on the face of thing on that, this works. So good. Here, I'd love to be happy about this, 100%, 87%. But you see, there are two cases. Maybe the model has learned, or maybe the model has just learned to replicate my generating procedure. What would I see? Exactly this. So there's absolutely no way to tell whether the model actually learns or exploits some kind of hole I would have left in my generating pod. So what I'm saying here is that this is totally useless. On those problems, you cannot do in-domain performance because backward generated data in in-domain performance, good performance will happen if you succeed and if you fail. If you fail in the sense that the model learns to inverse the generating procedure. Yeah.
Deep size 50 means you generate 50 solutions, one of them is correct.
Yes, exactly. There are guesses. I'm exploiting the fact that I have an external verifier. So if I have one solution, it counts. Yeah.
So I was a bit confused, but so what is exactly your training set?
So here the training set, I got 4 training sets, this and this and this and this. And every time I test my training set on held out data from the same distribution. So I'm testing this on data generated with the same system, not contaminated, but generated with the same. What I'm saying is that this in-domain performance, so here, this is good news because, there's no, you cannot invert a forward method of generation. So this is good news. It shows it works. But this doesn't tell you anything because it could work because my model actually learns to generalize to example it hasn't seen, or it could work because my model has just learned to invert the generating process. So the only way to test it will be out of domain. And that's easy. You test backward on forward and forward on backward. And on this, the model cannot cheat. The model is tested on backward, but the data that it will be tested on are not backward. They're really different. But the model will be penalized also because the forward data has a different distribution than the backward data. So the model is both not being able to cheat, but it's solving a harder problem, a problem which is out of domain. So what you see here is that on the forward data set, models trained on forward data set, tested on backward generated data, succeed, but to a low effect. And this is the out of distribution effect. So those guys, so they're relatively small models, well, trained on relatively small data, so they're not very good, but you can see that out of distribution, they don't work well.
Just to be clear, so
this is the train set.
All of these are solving the problem given F fine.
Yes.
Backward means
it's the training data. Yeah. Yeah.
And forward means just more sophisticated SLS tool.
Exactly.
Okay.
Exactly.
What was the course?
So the forward tool Forward means that you use source tools. So those are models you can solve with, those are examples you can solve with state-of-the-art methods, only polynomial and a special class of polynomial systems. This is a training set, this is a test set. So here I got two models trained on source tool data, which are FBAR and FLIAP, which I test on a backward data. And here I have two backward trained models that I test on forward examples. So
the forward examples are so restrictive that that's what motivated you to do the backward method?
Exactly,
Okay.
exactly. So what you see is that the forward doesn't generalize well because of the art of generalization problem. But the funny thing is that this works. So these examples are, these training sets are large. You can see that on the Lyapunov function problem forward, the polynomial and the non-polynomial, so trained not on polynomials, are able to achieve 70% accuracy, which is quite good.
Sorry, just again, the non-polynomial means polynomials and non-polynomials, right?
In the non-polynomial, you have some polynomials in, but it's mostly non-polynomials. But they're polynomials of different things, so they share a common structure.
So I presume if you look at the two distributions, they're pretty obviously different.
Yes.
Is there a sort of an obvious sense in which those the problems that generated by backward are actually harder than the problems generated by forward?
So as a rule, the problems generated by backward, they're very different. It's difficult to say that they're harder or easier, but they're very different. So you see this with a very bad generalization. So what you can see is that this seems to work. It's only 75%. We would have loved to have better, but it sort of works. And these are easy problems. So we expect decent result if it generalizes. Yes, Leo.
The FEF are polynomial.
FLIAP, yeah, all those are polynomial because I can only solve polynomial.
So basically, when you train on non-polynomial, it's slightly better on the polynomial.
Yes, we've been saying that. We've been noticing that. So it's close, but we've been observing the close result many times. So it says that a more diverse training set seems to help, and it's been observed a couple of times. I wouldn't draw a very strong conclusion out of that because it's small difference and small test sets, etc. But it seems so. What's also funny is that you see those are the barrier functions. So it's not the same problem. It's a related problem, but a slightly different one. And you still achieve some kind of accuracy on these guys, which in itself is surprising. Yes?
In this case, it means it finds a barrier function or it finds a positive.
No, it finds a barrier function.
But you never train it with fine.
No, I didn't train, but barrier functions are very close. They just differ on the fact that it's a local minimum. So a Lyapunov function is a barrier function. So if it finds a Lyapunov function,
So that was my question. Does it find the Lyapunov function?
I suspect it finds, most of the time it will find a Lyapunov function because it's trained to do that.
Which it didn't have.
Yeah.
And
Okay, so, yeah.
Pretty much 100% generate sensible.
Oh yeah, all these functions have a minimum and
Yeah, but that farms.
yeah. So
And what is like the typical depth of the functions in terms of the tree?
in terms of the free tree, I think it's like, well, for the polynomials, we don't really have a tree, but
And what's the degree?
yeah, they're not, the degree is between 2 and 5 all the time.
Why do we test on something like the forward ones? Because when you test, you generate reported Lyapunov functions that are not going to be ones that are in the 400%, but that you're going to check.
So the thing is that,
Random Fs and no.
yes, we'll see that in a while. The thing is that I want to generate those functions because I want to test it on stable Lyapunov systems. And the only way to have a stable Lyapunov system is to know a Lyapunov function. It's that thing where, but we'll see in a while. I'm going to show you what happens if you generate random functions. So we get something that sort of rules out, the idea that you have, that the model is inverting the generation. Yes?
To go between 5% and 100%, is there any sense in which you can characterize the examples in which it fails and see whether you're properly corrected or you're backwards?
So yeah, we looked at the failure case and it wasn't very obvious, but you'll see in a slide that we have a method to improve it greatly. So we have an idea of why the failures happen. So this shows that probably the model is not just, inverting the generative procedure. Something is really happening here.
If you look at a different size, different.
Yeah, so obviously, you know, the larger the system, the more difficult it is.
But also experience size of the model.
Yeah, yeah, the size of the model, the length of the sequence plays a role. It was a bit difficult to characterize because yeah.
There's some elementary statistics on the size of the formulas in, let's say, FLIAP and POLY.
So I think we have them, but I don't have them here. But I can send them to you. So the thing we have here is that we see we're at 75, 73%. It's interesting, but we're also solving an out-of-domain generalization. And I'm very happy we have Sami here because now it's the homage to Sami. Models trained on B-poly achieve 73% accuracy on forward. Okay, but parts of the failures are necessarily due to the fact that my test set is out of distribution. So it would be good to eliminate this. And a year ago with Sami, we had this paper where we were wondering about how you can length generalize problems. So suppose you train a model to add numbers and you have small numbers. Can you generalize to large numbers? And it usually doesn't work. And one thing we showed was that there was a technique which we call priming, which says if you add just a few examples, a very small number of examples of long integers to your thing, then you solve a lot of problems. So the idea we have here is we could use priming here by saying, okay, we have this big B-poly sample, you know, backward sample. But I could also take a few elements from my forward samples, you know, my special things that source tool can do. I could take a few one and add them to the training sets. And here's the example. So if I have no mixture, I get a result of 73% accuracy. Now, suppose I add 100 FLIAP elements, so forward examples, to my training set. I remove them from the test set, of course. I add 100 of them to 1,000,000 examples. So that's 0.01%. That's a drop of water. You see the performance, it goes for 75 to 82%. So this gives you, and if you increase, you will go up a little, up to 1% here. If you add F bar, 300 example, you go to 83. But the funny thing is that you also learn the second task. So this is a bit like few-shot learning, if you like. So the fascinating thing here is that, yes, we have a problem with out-of-domain generalization, but there's a very easy way to do it. You know, we take just a few examples, easy examples that we know how to solve, and this would exist for many other problems. And we just dump them into the training set. And we don't need many of them. So if, you know, solving these examples are special examples and they're difficult and all that, then it still works. Okay. So you see the results we get. So just to compare the state of the art. So this is what the AI method gets on those different data. This is our model with the priming. So this is the kind of results we managed to get. This is what source tool would achieve. So the classical. So we're clearly beating the state of the art here. There's no debate about it. It's not, you know, it wasn't the goal. So what have we learned so far? We've learned that if you train on backward data set, you can generalize to generate polynomial system that source tool can solve. This works. We show that we can improve performance through priming to allow generalization to even related tasks, you know, to the barrier function. And we do better than AI methods. But I'm sort of cheating you. I've been telling you I'm solving an open problem. I'm not solving an open problem. I'm only solving on the things I knew how to solve right now. You know, I'm only testing on the data that source tool can do. So, you know, as the French say, tout ça pour ça. We haven't gone into, you know, the real difficult part. So the last part of this talk, we get into the wild. So we do exactly what you suggested. We are generating 3 sets of random systems with a local minimum in 0. So we apply, you know, the Jacobian eigenvalue property to check that we have a random, a local minimum. And we generate 3 sets, poly 3, poly 5, non-poly, of polynomial system of degree 2 and 3, 2 to 5, and non-polynomial. Systems that look like, for the non-polynomial, that are similar to the one we generate, so with the same operators, etc. Model is not completely lost. We have no way to know how many stable systems there are there. So we're expecting very much lower case because many of those systems have no Lyapunov function. So there's no way we will find one. Okay, and we have no way to know what are those values. So here's the state of the art. So we have we made big sets because we had no idea of how many examples we need. So 60,000 for the polynomial, 20,000 for the non-polynomial. So SourceTool only solves 1% of those. Okay, so SourceTool really struggles. We put a time limit. If we had a longer time limit, it would be better, but it really struggles on those, which again shows that SourceTool is not solving all the polynomial system. We don't know how good and bad this is because we don't know what the value is. But if you look at the other AI method, one of them does better. It gets 2 or 3% accuracy. Yeah. And then our method are here. So you see we can find about 10% of them. We don't know if it's good, we don't know if it's bad, and we have no way to know.
And can't you just simulate these systems?
So we probably could, and we probably should. But practically, you know, we were quite happy about that, I must say. Yes, Leo. Yeah, even the forward model works well. You see, the backward model works, but the forward model, but the problem of the forward model that it will only work on the polynomial. So this is an interesting takeaway. This is say, okay, you train on SourceTool elements, but you manage to be able to generalize to non-SourceTool things better than SourceTools. So there is something on generalization here that does happen in the polynomial model. Yes.
Where does the transformer output in case where no function exists, that it outputs something that's
it always outputs a solution, and the solution is false.
Okay, so not just an empty string or something, it outputs.
No. It outputs a solution. It always tries.
Yeah.
You know, it's like ChatGPT. ChatGPT always tries to give you an answer. That's the same kind of idea. So what I'm saying here is that we don't know if these results are good, but we see they're much better than the results are there. So there's a very strong intuition that we are indeed solving an open problem with that. So as before, we can do priming. You know, priming works all the time. So you can take a couple of wild examples that the model can solve and add that to the train set. You remove or you regenerate a new test set to have no contamination, and you rerun. And if you had 1,000 wild examples to be poly, so 0.1%, you get up from about 12% to 13.5%. So this bootstrapping system works again. We didn't push it more, but this gives an idea of, you know, what could be possible there. So I'm done with this. Last question. I haven't talked about the humans, but we were lucky because Amaury is a professor in École des Ponts, and he teaches students Lyapunov functions. So he used this opportunity to test. He designed a test on 75 SourceTool function to his master students after a semester on Lyapunov function. So all the students had 3 examples that they needed to solve in 30 minutes. Student performance for around 10%. So, yeah, I don't know if it tells something about the students or Lyapunov or the difficulty, but yeah, but for polynomial function, there are ways you can do by hand, emulating SourceTools, etc. So they were relatively easy problems, but then, you know, there was only half an hour for 3 problems, etc. So I'm not claiming anything here, but that's always fun. So just to finish, my conclusion from that, wondering out loud. So we managed to solve random problems in the wild. And this is important. We are able to have functions that no one knows whether they have a stable Lyapunov function, but we found some. So this is good. We're solving an open problem. What we haven't done is solve interesting problem. And yes, this is pure provocation compared to what was said on Tuesday. What's an interesting problem? In real life, what would happen? We would have mathematicians coming to the model and say, this is a subject, this is a model I want to study. And we really need now to see, you know, how the model performs, not on random system, but on system that educated people have, or people who know the area would like to see solved.
So, set up a website. Set up a website.
Yes, it looks like a good idea. So there are 3 things I'd like to mention. So the first thing, which should be obvious, is that generation is the hard part. And we have no systematic way of doing backward generation, and we need that. So that's a field of research that needs to be explored. There's no way out of it. And this is more on the side of the mathematicians, because the real problem in backward generation are not, computer problems. They're really mathematic problems. Also, I've been talking all the time of in-domain, out of distribution, etc. I never said a word about what the distribution were, because I don't know. And we've been saying that many times. We need to get a theory of, this notion of distribution of problems that appear all the time when we do AI. And again, we don't have the beginning of a theory on that. So yeah, that's another job for mathematicians. And finally, you see the work of priming and bootstrapping. And this is more for the AI people. It would really be worth, studying those. Okay, so I'm done with that. I got a few more slides that Jordi wanted. So Jordi, it's up to you. Do you want me to present them or not?
Is this the multiplication?
Yes.
I think it's very nice.
Okay, so I'm going to talk. I'm sorry, I'll be a bit off the time. I'm taking on Jordi's time, so all your fault. So I'd like to show something slightly different. So these are current results. I'm working on that. The paper is not even written, so it's just observation. But it's observation, I think, that are important on how mathematical problems are an interesting AI benchmark and a very good way to learn things about AI. And it's something that I think mathematicians or mathematicians interested in AI should own. So I'm interested in something I call the low data regime. Let me explain. When you train on mathematical problems, you generate your examples. I've been saying that a lot. If you train on easy problem, it's very easy to generate examples. So you can have as many examples as you want. So, the idea is that you can get tens of millions of examples. You can get as many as you want. So you always do. What if you didn't? What if your examples were limited? So common wisdom knows that. You don't even have to think. You listen to others and it says, oh, bad thing. You don't want to have small sets, because if you have a small set, you have a problem with example diversity. You have not enough examples to learn all the edge cases. So that compromises your learning. And second, if you have too few examples, you're going to repeat them. And then overfit will happen, and overfit is bad. We all know that. So this shouldn't work. Nevertheless, it's interesting to look at what happens. So I'm looking at one math problem, which is learning eigenvalues. So you give the model matrix, 5x5 matrix, and you have it predict the eigenvalues of the matrix. Again, as sequence of data. I have a paper on that, and this works. So you have two cases. If you have unlimited examples, you can see this is a train loss. So these are the unlimited examples. So you see that my model are slowly reducing the train loss, and at one moment, the model gets it, so the loss drops. And at the moment the model gets it, the test loss here goes with the train loss, it's normal. And at the moment the model gets it, the model learns the eigenvalues, the accuracy goes up. And the model that couldn't predict the eigenvalues suddenly learns how to do it. The time when it happens is very variable. It depends on the initialization of the model. I don't have the beginning of the theory of why this happens, but this I observe. What happens now if you have 100,000 examples? Well, you see that you get a drop in the train loss that is very, very fast after about 5 epochs, very, very fast here. And at the time you get this drop, the test loss goes up. The test loss goes up because you're overfitting your training data, because you've only got 100,000 of them. And because you're overfitting, you never learn. Because once you overfit, there's no way of learning. Okay, so this is exactly what common wisdom say. So why am I showing you that? Well, now take an interesting case where you have 200,000 examples. 200,000 examples, you're going to have overfit, but a little later, about 10 epochs, not 5 epochs. So about 3 million examples. And 3 million example is the time where usually models begin learning. It varies a lot, but that's what it takes. So here it's interesting because you can see my train loss. It goes down. Some models go faster, some models go slower. Okay, things vary. But then you can see my models, I really have two classes. I have models that overfit very fast, and I have models that don't overfit and overfit later. And if I look at those models learn. So what happens is that when overfit starts after 3 million examples, and this is standard, some models have started learning and some models haven't. If the model haven't started learning, they're doomed. They will never learn because overfit is there. If the models start learning, you see there, it goes down and overfit disappears. It doesn't disappear. The model learns and overfit is delayed because you can see here that some of the curves drop. This is because of overfit, but later overfit.
And shouldn't the model, the task have some sample complexity, some.
So the number of examples is around those 200K. I experimented with that, but since the moment when the model overfit is variable, you never know exactly, so you can play with it. But the funny thing is that when you look at it, it says that there's more to overfit and learning. That's what people usually say. What I like to think of, the way I like to think of it is that they're very related. Once a model overfit, it doesn't learn, learning is cancelled. But once a model fair, overfit is not cancelled, but at least it's delayed. So it's a bit more complicated than saying small samples, large sample, overfit, etc. There's a weird relation between overfit and learning.
Correct me if I'm wrong, but I was not surprised because I would have just said, well, this is a task, it's got some sample complexity. If you have to sample, once you get there, there's a chance of learning.
Yeah, but the fact that once you learn, the number of examples and your resistance to overfit changes was sort of news to me. I wouldn't have expected that, to be very honest. But going on with that, so I'm changing problem. I'm looking at the GCD problem. So I'm giving pair of integers predicting the GCD. And the indicator here is the number of GCD I'm able to predict out of the first 100. Okay, so now I'm training from 30 million to 1 billion examples, so very, very long time, stopping at times to see what happens. And I'm training model on 1 million, 5 million, 10 million, up to unlimited examples. Okay, so what you see here, after 30 million examples, most models predict about 13 GCD, but 2 models were better. They are the small models. So smaller is better, they learn faster. If you go to
accuracy,
this is the number of predicted GCD, so it's a proxy for an accuracy. Yeah, the GCDs are predicted one by one in this example. So I count the number of correct, if I take all the GCDs of all the numbers between 1 and 1000 in my test set, I have a huge test set. I count the number of GCD that the model is able to predict correctly and the number that it never predicts correctly. It's a slightly better proxy. So if I wait for 300 million examples, you can see that the best model now is the 10 million, followed by the 5 and the other one. This one has overfitted, you see it here. So it's lost because overfitting breaks everything. But the best model is this one. And if I wait for 600 million example, the best model is the 25 million example. But the fun thing is that the unlimited or the 100 million example up to 1 billion, they're never good. So what I see here is that the best models are not the models that are trained just see many examples just once. They're models that are trained on smaller samples that are repeated so long they're not repeated so much that they overfit. So it seems to suggest that small models do better. And I can reproduce that for modular multiplication. So here I'm multiplying A times B for a number between 1 and 1 million, modulo 67. What you see is that this is the number of models that can predict. Most of the time, the models don't predict. And infinite or 100 million data, they never predict. And I thought it was impossible. But then I noticed that when I work on data constraint data, then in some case, the model managed to learn modular multiplication. Okay. A fun fact here is that the way they learn, this is the learning curve, 80 learning curves. I'm showing that because of the flat lines. You see, when the model learns accuracy, it learns up to a certain value. And the values are quantized. Basically, the model cannot learn any kind of value. There are specific values that the model learns. And I can explain those values. Those values correspond to the divisors of p minus 1, so 66. So there is some kind of a link between that I don't quite understand. But there's an interesting phenomenon here. I'm showing this because it's fun. But practically, the conclusion is the same here. If you restrict the data budget and you have repetition, then your model is going to learn better and faster. So I'm almost finished. The thing is that suppose now, I think the other way around. Suppose I have 100 million GCD example, and that's all I have. What's the best way to use them? Do I want to see them, all the same number of time? Or would I like to take a small sample of them and repeat it a lot, and the others I don't repeat? So here is a small sample, is the size of the small sample. And here's the probability of seeing the small sample versus the large sample. So I'm taking randomly here 50,000 example in my 100 million. And those guys, I'm going to see a lot. And the rest, and I see that if all my samples are recurrent probable, above 600 million examples, I learn about 35 GCD. If I select 50,000 examples and show them in one case out of 4, and this 3 case out of 4 are the others, I can learn 69 GCD in the same data, in the same training budget, in the same compute budget. So there's a big difference just by splitting your sample in 2 and having a subsample, a small sample on which you repeat a lot, and 1. So repetition seems to help. And yeah. And it's interesting because you can repeat that for many things. So these are the case where you train on 1 sample and on 2 samples. So the interesting guys are those. You see, so it learns by steps. So this is, as before, everything is quantized, but the GCD works like this. The funny thing is that if you have only one thing, you will probably eventually achieve the same level, but it takes more time. So it's the same curve, but having repetition speeds up learning. So if you have a fixed compute budget, you want to have a small sample. This helps. Okay. And finally, you might say, okay, now that I know that the small data budget is good, why take it randomly? Let's use good case. Let's do curriculum learning. Let's select cases that are better. So I tried a number of things for a number of good reasons here. The point is that it doesn't work. Well, it doesn't work. It works just as well if you select randomly elements. So what I'm saying is that, repetition sort of trumps curriculum on this, in the sense that if you repeat elements, a small number of elements, you get better results. So what you see here is that, a small training set and repeated examples seem to help. I've seen that only on mathematical examples, but it's quite possible that the thing holds elsewhere. The difficult thing is that it's very difficult to do in language model, because in language model, how do you measure repetition in a train set? You can't. Yes, Leon?
I can give you an example of this from very old times. Small clarity problem, XOR problem. 2 inputs or 3 inputs, 1, 0, 1 minus 1. You want to compute 2 sides of the problem, essentially. It's 1 minus 1. We know from since Minsky and Tucker, this is hard to train. That's a trend. But with a 2-layer network, you can train. Take a small 2-layer network, so it's quite hard. And if you sample them equally, you do quite a sense. Yeah, it's going to work, but sometimes not work. It's not very reliable. If you debalance the training set, I mean that now some of them are more frequent than others. So basically, you sort of asymmetry saddle point. Works much better.
So I want this reference for the paper because it is exactly it, right?
Maybe there is a guy who, maybe there is one long after. But it's something that we noticed at the beginning, that sometimes when you do things equally, the only thing you're doing is that you're putting yourself on a saddle point. That's pretty difficult to get out of. And if you start by saying, start with this, whatever it is, and then expand.
Which is sort of what we get here. Yeah.
So this is why I told you to look in the training set. Which proportional examples are properly recognized.
Yeah, I totally agree with that. We should look at which one I learn first, and what are the accuracies on both sets. So smaller train set work for a fixed data budget. Splitting is a good idea, and you don't get a lot of traction from curating the small set. What's interesting is that doing this on mathematical problem, it's very easy to control everything. You can control the data, you have the theory, you can absolutely know. If you were doing that on LLMs or something, how do you know repetition on scraped internet things? It's full of duplication. There's no way to measure it. It's impossible. And how will you do that on trillions of tokens? So what I want to say here is that it seems clear to me that you can get a lot of learning on AI done by carefully selecting your mathematical examples. Yes.
Anecdotally, I've heard that serious big language models do take subsets of the corpus and train many times on those.
Yes, but if you look at their tech reports, because I read all that, if you look at the tech report, the tendency is more less and less and less. So something are seen only once, But the Wikipedia or stuff like that is like 3 times or maybe 4 times. Here with my 50,000, it's like 3,000 times. So it's really different reading. But there was a paper in Europe last year, a guy who said, for pre-training, you could repeat things 4 times and it's better. You got an inaural or maybe a best paper in Europe or something. So people are beginning to study this. What I'm claiming here is that, math are the perfect benchmark. So I'm done, and Jordi, it's yours.
So here there are a lot of questions on the chat. Sorry, I mean, should I ask them, or do you have time, or it's fine if you ask them?
Yeah, no worries.
Okay, I will take a few of them because there are lots here. So the first one is by Jordan Ellenberg. So the question is, when the dynamical system given by F is actually unstable, does the outputted V typically have any relation with F? For instance, if grad V times F is grad V times F is the negative, or is it basically random out?
So I haven't checked that. I would expect they are sort of random, but I would need to check that. I don't know.
This another question, which is like, okay, you mentioned beam search. Can you give a bit more details about it?
So the beam search is very easy. In that case, there's no sampling, nothing. We just take the first probabilities in the logits. So you get n values, then you get the second probability, so get n squared and calculate the perplexity of both, and then keep the n first and so on. So it's the most stupid approach to beam search possible.
Maybe okay, another
And
question.
it's a top K, basically.
So can you give like details about the encoding? How did you guarantee that the output of your language model was a valid function?
So I don't. I absolutely don't guarantee that they're valid. If it's invalid, it's just false. But practically, the reality is that the model learns syntax in no time. So all the functions decoded function, or 99.9% of model prediction, even when there's no solution, decode as functions. It's I have no explanation. It's something I observe all the time.
The last question, maybe. So for your last part, what you are showing, does it run? I mean, is it like countering like grokking? Like, how can you explain the relationship of what you are showing with grokking?
So it's not grokking. It has. I like to talk about grokking because I see the steps, and the steps look like grokking, but it's really not grokking, because grokking is something happens when you overfit. And here there's no overfitting except in the very beginning, but I didn't see grokking. When I overfit, everything was dead. So I didn't have grokking. Maybe I didn't wait enough. So the steps I have are not grokking in the sense that I don't have the preliminary overfitting that happens in grokking.
Maybe like just to expand on that, grokking typically concerns very small data sets and very heavy training regimes on very small data sets, whereas you're considering modular multiplication of very large numbers modulo some small prime.
Yeah.
And so the training data set is kind of almost infinite.
Yeah, the problem space is 10 to the 12. So I never reach it. Yes.
I just had a question in terms of Lyapunov's theories. How is that applied to robotics or AI? I'm looking at the practicability.
So the way they use control theory and Lyapunov function, as I said, it's about control. So the idea is that in reality, the system you have is a system which is dependent on a number of parameters, which are functions typically, which correspond to things you can act on. So you can think of think of a satellite. So the satellite has a certain law, and there's a law which includes a parameter, which is the engine. Okay, and you want, in that case, or when you have a robot, you have a dynamical system of the robot plus the engine. Or when you have waterways, you would have the locks and the things you can do on the locks and the waterways. So the way you apply it is typically you want to plan interventions. This is Kalman theory. So you want to plan interventions that will put you in some future equilibrium, and you want to check that this equilibrium you arrive at is stable. Because if you intervene on a system by starting the engine of the rockets or something like that, you are going to try to go from one equilibrium to another. And of course, it will be approximate. And if it's unstable, anything can happen. So what you want to say is that using control, you want to guarantee that the like throughout the pass and at the end of the
And you
pass.
have to always adjust it, continue to adjust it like.
So this is, so this is exactly the point of, small control, like the neural Lyapunov and the large control. If you have a global Lyapunov function, you're safe no matter what you do because everything is global. If you have a local thing on small intervention, then the hard problem in that case is not to find the Lyapunov function, but to find the bounds. And this is what the neural nets do. So they're really solving a different problem. What I'm trying to say is that I know that my system is stable by small intervention, but what exactly is small? Or how large the small could be so that I'm still safe?
Thank you.